All right. Good morning, everyone. Um, yeah, Heather. I think there were some issues on Tuesday too. I think the internet is seeing a little more than normal use during business hours. Um, Again, hopefully these things get recorded so you can always go back and look at them in retrospect. The original idea was I was going to record videos and assign them, but I figured having the questions would help, and it has. It has definitely stopped me from making a mistake re-recording and re-recording, and also has had a bit of interaction. Um, let's see. So we're moving along fairly well. The exam due date is coming up in 4 days. So try to get the exam done. Please email me if you have any questions. It's on the word problems. I'm actually going to look at one of the questions that came up. Two of the questions, one from Janine and one from Alec. Here, and then we're also going to look at well, something's up with the audio. What's happening here? Where's the audio? Can you guys hear me? Let's try that again. Hmm. Okay. Oh, you can hear me? All right. All right. Sorry about that. My stream is saying that, let me come back here, that the audio bit rate is low. I think that was just, yeah, that was when I had it muted. It wasn't seeing anything. Okay. Sorry about that. The dramatic pause. Thanks. See, this is what's good at having interaction here. I had done a couple of videos as answers to questions, and the audio wasn't working, and I don't hear the playback. I posted them up, and then I went back checking things out and realized they were dead silent. So it just looked like me scratching on a piece of paper. Um, okay, so the exam due date is up. It's on there. There's multiple attempts for the exam. If you're having any problems with it, please let me know. Email me, email me, email me. Email is flooded right now. I'm getting back to everyone as much as I can, as often as I can. A lot of times I will, if someone asks a question, I'll answer the question for everyone. Um, Coming across. I'm going to keep recapping this, so let me go over here. I think through repetition, we can see some things a bit better. I think this is where I want to be, and come to here. I have a playlist, and the link for the playlist is up on Blackboard, the link back to the playlist. And so I will be putting any of the videos into here. And so they get stored into here. So if there's anything you missed, you can come back and watch. Now, that itself, the link back to the playlist is in Blackboard in course content under running schedule, where I have the major due dates, the practice exam, and the real exam. And I actually think it's 20 questions. I think I lied. I didn't think it was 15. Shh. But I didn't choose the hardest of the questions. And then the link to the playlist is down there. I've also am putting all the PowerPoint lectures up by chapter and section. So if you want to study off of them, they are all on Blackboard. It's making the link to it that's a little hard right now. And so I'm going through and just kind of in between things, going through and making these links. I also have the practice worksheets we used in class are here. Now, the thing I have to do is change the chapter numbers to match what's in the book. I'm using this is the chapter numbers on the online version, and we're good up to chapter 6 is the same. Chapter 7 in our printed book is chapter 11. So this is 7, 8. Let's see, wait, no, I think 7, 8, 9. 7, 8, 9. Yes, I think this would be chapter 7 in our book. No, it is, yeah. See, and this is the problem with that book here. This is chapter 7. In the printed book. So 7, 8, 9. 10. So I will get the chapter numbers updated. But these were the worksheets we did in class. That was the in class. I will make a link to the ones that we're working on. Basically, I'm waiting until this exam is done to start throwing the next bit of in-class material at you. Let me switch back over to here so I can see here. All right, there you guys are. One of the things you'll have is, if you just to show you what I'm looking at, this is I have this screen here that shows me the status of the stream, and I can see your chats over on the right hand side. Well, all of my other windows sit over top of this, so I see this on the side. But when you hear me pause sometimes, I have to open up my software to switch things, and then switch the windows. And you probably hear my mouse in the background as I'm going. So I apologize for all of that. All right, now I need to find my pen. All right, not much heavy lifting today. What I really want to explore is the idea of a linear equation where we have some number times a variable plus some number equals another number. But we're going to trick it out here. We're going to do something so we can talk about any combination of these. And it's a neat trick that we're going to work on. Because what we're going to do is we're going to introduce a second variable so that things can vary and we can get an infinite amount of answers for us. And having an infinite amount of answers isn't a bad thing. It can talk more about the descriptions of things. So, for example, if I have 3x plus 4 equals something, my c, so I'm taking this form and I'm coming down, I have 3 times x plus 4 equals something. Well, I can find out all the possible somethings. That's going to be our goal, is how we can talk about it. And then we can then say, hey, you know what? Something about this and this are different than if I had 1/2 x minus 3 equals something. And so we can start describing these expressions. If we can talk about every possible value they have and why they're different from each other. So one of the things we're going to build, I'm going to get a completely blank screen. So this is where we're going. And we're going over this probably about 3 lectures. This will probably take us halfway through April to really explore what this means. And then we'll be ending with kind of the things that come out of it. So I'm going to scroll up here. I'm going to make something that we have. Oops. Let me make a line. And this is our friend, the number line. And I'm going to put, for right now, 0 in the middle. And I'm going to give even parts. So give me a second to draw up here. So work my way through. This is the number line. We've been using it to compare the value of numbers that we could have. See how good my drawing of intervals are. Yeah, that one's a little wide. But this will work for now. I have a more accurate one that I'll be using shortly. And this was our real number line, and we could say each one of these was a unit. So 1, 2, 3, 4, 5. That's 5 over 1, 2, 3, 4, 5. That's 10 over, and things moving to the left are negative. 1, 2, 3, 4, 5. So that's negative 5. And things moving to the right are positive. Left negative, right positive. And so our number line was a way of comparing values that came out. And in the 1600s, mathematics was usually linked to geometry. Anytime you wanted to prove something worked in algebra, you had to come up with geometry for it. Because this was happening a lot, Rene Descartes, the I think therefore I am guy, decided to take numbers and this idea of a number line and make them geometric. And so what he decided to do was say, hey, I'm going to let everything in this direction, left and right, get the variable x. And I'm going to put this little hat on top of it to say, hey, I'm talking about everything in the left-right direction. And then he came around and said, well, I'm going to give it another direction, because if I want to talk about anything on the page, I can have another direction going up and down. So you can left and right, up and down. And so he put another number line that he also broke down. And it worked just like the number line going left and right, but it talked about things going up and down only. And so we're going to spend a lot of time exploring this because Descartes did this. This is called the Cartesian, and I'm not sure about the spelling. Let's double check my... So Cartesian gets this... Cartesian. Let's see if I can spell it right. Oh, there we go. Cartesian. Plane. And it's a plane because it's a flat surface. And what was nice about this was Descartes now had a way of attaching a number to any place. Now, we're talking about equations, and I've jumped over to talking about space and geometry. The things that we will get from this do not always have to be geometric. What Descartes is going to do is he's going to borrow things we already know from geometry and let us talk about numbers for it. To start, though, we kind of have to say, hey, what do we mean in geometry? And so one thing that these things do is these are at a right angle. So if I'm sitting at 0 And this place where everything starts is going to be called the origin, because it's where the numbers for x originate and the numbers for y. And he calls this y, this up and down axis y. And so we can talk about these things. Well, if I move up in y, my value for x doesn't change. By being at a right angle, moving up in y doesn't change the value in x. And moving over in x doesn't change the value in y. And so he said, hey, I can name any point. So we're going to call this a point. I'm going to change my color for point. Let's see, a point will be orange. So a point, he can talk about two values, the x value and the y value. Mathematicians would later find out that if you're talking about one variable and you wanted to name it on a number line, because a number line was in one dimension, you only need one number to talk about it. If I now want to talk about any unique place on a flat plane or in two dimensions, I need two numbers to talk about it. And if I wanted to imagine that this was inside of a room, if you look at a corner of the room, you can see that the wall goes up from the floor to the ceiling, and then there's two lines that come off of it to either side to create the what would be the pattern of the floor. Well, that's what you would do for three dimensions, and you would have three numbers to describe any point in space, and we usually say x, y, and z. So Descartes, by doing this, started to figure out some of the things that we're going to talk about dimension-wise. But for us, it's really nice on a piece of paper, which is where we do a lot of work, on any flat plane, so flat surface, I can describe any place uniquely by two numbers if my order is always the x value first, then the y value. So the origin has the numbers 0, 0, because I'm at 0 in the x direction and I'm at 0 in the y direction. I want to pick a point here, right here. Well, let me get this right. This point right here, and I want to describe it uniquely. Let's see if this is coming through. All right, come back. There we go. Every time I click off this one screen, it doesn't come right back to it. And give me a second here. Kicking my computer time. There we go. There's that. Come back. Okay. I'll make this smaller so I can reach it. Sorry about this. Having a hard time reaching that one screen. There we go. Now are you back? Won't let me draw. There we go. Oh. Definitely need an extra cup of coffee, eh? This point here, the thing I want to describe, I can talk about its distance in the x direction, which is left and right, and its distance in the y direction. So I came over 1, 2, 3. So I'm going to put a dotted line down here. And I'm going to put a dotted line over here. And if we measure its x direction, it was 1, 2, 3 over in the x, and 1, 2, 3, 4 up in the y. And so we name this point 3, 4. Now, no other point can be named 3, 4. If I want to name something 3, 4, 1, 2, 3, 4, I will always end up at this spot. That's what was so great about Descartes' system here, is that any place was uniquely defined by this pair of numbers, and they're going to be called coordinates. Co means that they come together, and ordinates is like ordinal on a compass, directions. And so whatever system we have, be it this XY system, or you can have weird things with angles and radii in them, as long as the things that mention the direction and the measure come in groupings, they're called coordinates. Our coordinates are a coordinate pair because there's 2 of them. All right, well, let's look at a different point in red. No, I'll go bright yellow. And I'm going to look for something similar to this. What if I came over 4 in X, 1, 2, 3, 4, and up 3 in Y, 1, 2, 3. So I'm here. And that point is 4, 3. So notice they have similar numbers, but they end up in different places because the order of the numbers matters. The order of the numbers tell you your space, where you are in space. And for in this case, it is in alphabetical order. X, then Y. And we learned the real number line first for our X values, and that went left and right. So this is how I remember which number comes first and where they go, is we learned this pink line first. And so it gets our X value. We're going to put something at a right angle to it, that's our Y. And our numbers come in that order, X, Y. And this led to what we're really going to explore as we try to figure out what it means to be linear into graphing. By letting each point represent a number, Descartes could do mathematics using these numbers to have a relationship. And that relationship could describe 2 variables. And I'm going to scroll up here. This is all going to whip away really, really quickly here. I'm going to breathe, and I'll come back to it. Well, here I have an expression. And so our game, well, hey, I called this an unknown thing. We're going to call this Y. And we end up being able to say Y equals, and I'm going to change my letters around, something times X plus B. And now we can talk about lines. And we're going to figure out this has meaning and this has meaning as we go along. But notice how I have 2 variables, and then these are constants. And so for an example, I'm going to come back down here underneath this now, and I'm going to say Y equals 3x plus 2. That was holding the spot where M was, and this was holding the spot where B was, but I still have these as variables. And the reason we're going to do that is the 2 variables can talk about my XY plane. So there's a lot of lifting we have to do here. We have to take this geometry and be able to start talking about points. When we start doing that, we can start talking about two variables. It's like, oh no, two variables, really, really complicated. Well, what we're going to do is we're going to borrow language, and we're going to borrow some things about this graph. So instead of having to calculate it, we can talk about it. We can talk about it just like we talk about getting up, walking to the kitchen fridge. We know that path. That path is something we have learned since we were babies, learning to navigate our environment. We developed language and systems to do that. By putting our equations onto a graph, all that language comes to us. I can talk about, well, this point is higher than this point. Well, higher means it has a larger y value. So by borrowing where things sit, we can talk about the parts of them just as we would talk about things we see in any geometry around us. And that was what Descartes wanted to do. There's actually a very specific mathematical thing he borrowed, which we will come back to, which is, I will again hint at this, but we're going to spend some time on points. Come back here to make sure you guys are still there. And there we go. This is what he wanted to borrow. Let me get an orange line here. Was by making these axes a right angle. He guaranteed that every point made a right triangle. And so there was this lovely thing called the Pythagorean theorem. Where the legs of a right triangle squared equals the hypotenuse. And here's my legs. There's my hypotenuse. And so he wanted to borrow this. But in doing it, he got more out of it. Right? We won't look at this for a long time. But that was his game. If I make these right angles, no matter what point I look at, I will get a triangle. And so underneath all of this are triangles, triangles, triangles. But we won't see the triangles for a bit. We'll see a lot of the points. And I'll show you the different triangle here by going in yellow. Right, and there's another right triangle. And so by forcing x and y to be at right angles to each other, he could build all these little triangles. The side effect of it was, if you move solely an x, it doesn't change anything about your y. If I move over here, I'll do it in bright green, but I only move in x, this point is 10, 3, or 4, sorry. Because I didn't go up or down. Notice how my language is coming back to how we maneuver through space. If I move someplace else and I don't go up or down, I don't change my y value. Conversely, if I go down but don't change my left or right, then the x value stays the same. So if I come all the way down to here, I'm still at 3 on the x-axis, but now I'm at -4 on the y. And so that's the game we're playing, is we can talk about the math as if we're moving on a piece of paper. So I'm going to draw another Cartesian plane, and we're going to look at some things that happen due to this origin and what the numbers do. And we're just going to get used to this new space so we can take the language we already have and we can start bolting it onto these things. So down we go. Give me a second to draw a new graph here. So that's my origin, 0, 0. Let me put a couple tick marks through here. See, I have my rulers to do this. Should probably just copy a bunch of them, but this gives you time to sketch things in your notes. At this point, I would probably hand out graph paper. We'll see there's some things we can do to graph. I know people tend not to like graphs. I like the fact that I can talk about math as if I talk about things around me. And so those descriptive words have meaning for me. I can tell that if something is increasing, that it's going up or to the right. And if something is decreasing, it's either going to be going down or to the left, because I have two variables that when they increase, they have a direction to them. And that giving it direction will give us some language we already have. But our job is to get used to this new place that we're at, which is this Cartesian plane. Boy, the left side of my x-axis looks a lot neater than the right. All right, and I'm going to put, let's see, I'm going to use in red. That's going to be my origin. So I'm just going to bring this over to here. It's the origin. And it's where all the numbers start, so it's 0 and 0. All right. Well, one of the things, if I write the one line down, it breaks it into an upper half and a lower half. If I put the y-axis on, it breaks it into a lower half and an upper half in x value. So on either side of my x-axis, I have positive y's above and negative y's below. On either side of my y-axis, and notice that's the word I have here, these lines, these number lines are called axes, and oh, don't ask me to pluralize it. But one of them is an axis, so this is the y-axis, and this is the x-axis. But things to the right of the y-axis have positive x values, and things to the left of the y-axis have negative values, negative x values. Well, notice visually, we have 4 distinct regions. So I'm going to number those. And we call them, we're going to borrow Latin, and call them quadrants. Right? We call graph paper quadrants. Now, there is a numbering convention that goes on with this. This upper right quadrant is called quadrant 1. And we're going to see why. We're going to come back and we're going to look at some properties of quadrant 1. But we do our numbers counterclockwise. If you want to think about it, take your right hand. I'm going to try this with the camera now. All right, let's see if I can get this on the screen well. Let's see, does that work? I'm trying here. Let's see here. This might... I've got a camera and a camera, so we're going for infinity. But I think I can do this here. All right. So there's the blackboard. And there's me. All right. I like infinity. Let me go to this window here. All right. So if I start here and with my right hand stick my thumb towards me, my right hand's going to go counterclockwise. back to this, that infinity, infinity. And so the direction we move is counterclockwise. For any Wiccans out there, the Widderskin's in counterclockwise direction, being the positive direction coming through. Counterclockwise in mathematics has been the direction we tend to move in. And we call it a right-handed rule because it is the direction we would go with our right hand, with our thumb sticking towards us. And so they actually say mathematics are right-handed. So if I'm moving in a right-hand direction, this is quadrant 2. This is quadrant 3. And this is quadrant 4. Again, we're just kind of looking at this new place that we've made. We've laid down a room, and we're going to look at the room and a map, and we're going to see what we can see in our map. And the idea is if I lay down these 2 lines, I get these 4 spaces. And so I want to give these spaces a name, so if I need to talk about them, I can talk about them. Well, numbers are different slightly in each quadrant. So let's grab a point here. In bright green, I'm going to go over 3 and up 4. So this point is over 3 in the x direction and up 4 in the y direction. Notice all the numbers are positive. In fact, anything I do in the quadrant, let's do another one. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. And so this is over 10, up 8. But again, positive numbers. So everything in quadrant 1, the coordinate pair, both numbers are positive. Right? So any of the numbers are positive. Anything in quadrant 1 is positive. All right. Let's go into quadrant 2. So I'm going to go back 3 and up 4. 1, 2, 3. 1, 2, 3, 4. Well, I went back 3, negative 3, and up 4. Well, let's go back 10 and up 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. And so I went back 10 and up 8. And everything in quadrant 2 has a negative x value and a positive y value. Again, I'm laying out the space here. Notice my neatness in lines. These should mirror each other. So I got a little dense over here. This is why graph paper is always better. Maybe I'll make a good graph paper. I'm kind of like drawing this out, though, as we work our way through. So I'm going to have to ask you if everything here is a negative x, and everything here was a positive y, and everything here was a positive x and a positive y, what are we going to get for quadrant 3? What would we see in quadrant 3? What values would we see hanging out in quadrant 3? Negative for x, y, both. Right? Yes. It'd be definitely negative x. And would the y be negative also, Teresa? Yeah. All right, that's not too bad of a delay on questions. I was always worried about the delay on questions. And so I'm going to do the same kind of pair of points here. I think I'll do it in orange this time. I'm going to go back 3, 1, 2, 3, and down 10, or down 4. 1, 2, 3, 4. And so that's -3, comma, -4. And I'm going to go back 10, 1, which will bring me here, and down 8. And that point is -10, comma, -8. And so this is kind of like an address system. And if you know your address, you can find the point. Well, without getting to the exact point, you know kind of the region everything is in, the zip code, so to speak. Right? This is the all positive zip code. This is the first number negative, the second number positive zip code. This is both numbers negative zip code. So over here, what is the x value? Is it positive or negative? On the positive or negative x's. Great. And then our y value would be? Our y value would be negative. Perfect. Well done. That's not too bad of a delay, I hope, and it at least lets us engage with the material a little bit more. And so this is the first number positive, second number negative. Notice the 4 quadrants give us every possible combination of negatives and positives. And so Descartes' goal here was to map space in a way that he could talk about pairs of numbers in coming into positions. All right. Let me just flip over here. Trying to make sure. Well, and this goes back to, we want to talk about the tables we did before. We kind of did a table a few graphs below. What I want to do is come down here and look at a table that we did. I'm just trying to find the table here, but it's okay. We'll make a new table. Give me a second to redraw my graph. I think I'll keep using pink on it. This is fun to watch me do it with the ruler on the blackboard, because I'll take my time to start out with, and then I feel like I'm leaving way too much of an awkward silence, and I start rushing, and my graphs never turn out right because of that. So online, I'm going, they can always rewind or fast forward. So I'll go slow, I'll go fast. I don't know. We'll get there. I'm going to try to make half decent graphs. But at least with the ruler, I have the markings on the ruler. The way my tablet works, I'm not 100% able to do that yet. I'll figure it out. I think if I can get my screen taped off on this, I might be able to use the ruler on it, okay? All right, we get used to our technology. I notice I like the sound of my voice so much that while I'm drawing this graph, I'm babbling very useless stuff so that you can watch the graph move with an audio track. Wait, maybe let's see. We'll get distracting guitar music while I finish drawing the graph. How's that? Convenient. Nope, that's not working either. There we go. I'll distract that there while I finish drawing. Be like my hold music. All right, that was the hold music. There we go. We have a graph coming through. What we're going to do is make a table of an expression, and then we're going to look at why this helps us here. And so, no, that's as loud. I was just playing it off of my phone. Sorry, I was kind of sort of teasing, put something in the background, and so I can maybe next time when I have that thing up saying audio will start in 5 minutes, I'll put that up since I own the copyrights on it. I won't have to worry about YouTube taking stuff down. And so let's look at the expression 3x plus 4. And one of the things we had done was we made a table, and I'm going to make the table kind of down here. We said, hey, let's look at what values we get. Actually, I'll just move this up a little bit. Yeah. I'm going to do some adjusting so I have some space. I'll do 3x plus 4 here is the expression. I said, hey, what happens? Well, if x is 0, negative 1, 1, 2, and 2. Those were the tables we made when looking at expressions. And so if I put 0 into this, 3 times 0 is 0, and my answer is 4. If I put 1 into this, 1 times 3 is 3, and 3 plus 4 is 7. If I put 2 into this, 2 times 3 is 6, and 6 plus 4 is 10. If I put negative 1 into this, that should be a negative 2. I think I overdrew it when I did this. If I put negative 1 into this, negative 1 times 3 is negative 3, plus 4 is 1. And if I put negative 2 into this, negative 2 times 3 is negative 6, plus 4 is negative 2. But notice I have an x value and an answer. And so what I'll do is I'll make my answer my y values. That's why we spend a little time doing these tables, because tables can help us talk about it. So I can say, hey, my y value is equal to the answer 3x plus 4. And so at 0, my x value is 0, my y value is 4. So that's the point 1, 2, 3, 4. And so I'll go, hey, I'll point to the point. That's 0, 4. If my x value is 1, my point is 7. Whoops, that's not quite on 1. 1, 4, 5. Keep jumping a little bit to the right there, so I'm going to overcorrect and see if that works. That does it. And if I'm at 2, I'm at 10, which is up here-ish. And negative 1, so negative 1 for my x value, 1 for my y value. Negative 2 for my x value, negative 2 for my y value. And I'm going to use a light blue line here. Notice what these do. They kind of sort of make a line. They would actually make a line if I used graph paper, right? I was drawing a little crooked here. And so this goes back to why we're calling these things linear equations. Any x value I pop in kind of lies on the line. Not kind of, does lie on this line. And so if we can make these tables we made before, we can start filling in the parts of the graph. Well, why would you want to do that? We can make the table. But what's nice is that we can talk about what this thing is doing in its very general term. Notice, as my x value increases, my y value increases. It's increasing or rising. I can say that visually from this. By graphing this, I have this visual relationship. Well, I know if x is 1, y is 7. If x is 2, y is 10. Well, if x is 1/2, my answer's somewhere in the middle. And we can find values by finding where their x and y values touch the line. So there's a lot of utility we get from this. But I think the really neat thing is I'm going to graph another one here. And I'm going to just change one thing about what I did over here, and we're going to compare the two things. So I'm going to use bright red, and I'm going to look at negative 3x plus 4. And I'm going to do the same table. All right, so we're going to say y equals negative 3x. And I'm going to do my table of x values. So my x is going to be negative 2, negative 1, 0, 1, 2. In my y value, okay, let's put 0 in. 0 in for x gives me negative 3 times 0, which is 0, plus 4, that's 4. Negative or positive 1 times negative 3 is negative 3. Negative 3 plus 4 is negative 1. 2 in for x. 2 times negative 3 is negative 6. I get negative 2. All right, do my negative numbers now. Negative 1 times negative 3 is positive 3. Positive 3 plus 4 is 7. Negative 3 times negative 2 is positive 6. And positive 6 and 4 is 10. So let's plot these points. I'll start with negative 2. It's up here at 10. Negative 1, which is up here at 7. 0 is at 4. 1 is at negative 1. Whoops, I'm sorry, 1 is at positive 1. Let's do that again. 1 goes into here. 1 times negative 3 is negative 3. Negative 3 and 4 is positive 1. That's better. And 2 is at negative 2. This makes a completely different line. And I'm just going to... And notice this line is decreasing. Oops. Or sinking. It has a direction on it. And so I can compare this to this visually. Something about this makes it decrease as I move from left to right. Something about this makes it increase as I move left to right. Well, what's the only thing I changed? That sign in front of this number. And so this number in front has something to do with how it rises or falls. And so we call it its rate of change. So that's the pattern we're going to look for when we do graphs. But a lot of things we can do is do tables. All right, I'm going to do one more table of something we've looked at loosely and show you how nice the tables can be for us. Now I'm going to look at an expression that isn't linear because I just want to show the usefulness of graphing. And I have an expression where I'm going to have x squared plus x. I don't know what this does. Well, I do. I've seen it enough. But just looking at it, I'm not 100% sure what it can do. So I'm going to make a table of values. So I'm going to say, hey, I'm going to let u equal y so I can plot you in space. And then I'm going to make a table of x values and y values. I usually start with 0 because 0 is nice and easy to calculate. And then I'll do 1 and 2 on the positive side. And I'll do -1 and -2 on the negative side. So if I put 0 in for x, 0 squared is 0 plus 0. That's 0. If I put 1 in for x, 1 squared is 1 plus 1 is 2. If I put 2 in for x, 2 squared is 4 plus 2 is 6. Now again, I'm doing these equations quickly. I expect when you're doing these on your paper, you'll go like, hey, y 2 squared plus 2 is 4 plus 2, which equals 6. I want to get right to the table, but when you make the table, you can do the other points. And so if I'm doing -1, y equals -1 squared plus -1. -1 squared is +1. And plus -1 is 0. And the same thing with -2. -2 squared is 4 plus -2 is 2. All right, and this is why we have our calculators here. We take our time. Remember, when we're doing things with exponents, always use your parentheses. But let's plot this. So at 0, I have 0. At 1, so I'll make this 1 and this 2, this -1. That's a little far over. -1, -2. So at 1, I go up to 2, which is here. And at 2, I go up to 6. So 2, 4, 6, which is about here. At -1, I'm still at 0. And at -2, I'm up to 2. And notice this thing comes down, does something, and goes back up. And so if we use these points, we can get a shape for it. What I'm going to do, I'm actually going to go to a graphing utility and show you what this looks like if I plot every single point possible for this. And there we have every single point. It makes this funny looking curve. And there's my -1 equals 0 and my 0 equals 0. And so this ability to graph, we can describe this thing. There are things that we can get out of x squared plus x that we might not see just looking at it. The fact that it turns around, that there's a smallest value, and it comes across. And so graphing lets us describe these things for any possible number we can put into it. But our job right now is to start building these tables. If we have some expression, we find the points to put it on. So we need to yeah, it is kind of a sloppy curve coming across. But what I wanted to show was that we haven't done anything with x squareds plus x's that often. But we can make a table and we can start getting a graph for it. We can look at values and start seeing how it moves. And that's what Descartes wanted with these spaces. The formula for slope, yeah, that's in the next lecture. Right now, we're just looking at the space. And I'm pointing out this rate of change or slope is coming up. For us right now, my big concern is that we map space to point, and we can take any expression we have and turn it into a set of points. We will talk about specific patterns in the following classes, specifically what are lines and what are parabolas, which we saw there. We kind of end with the quadratic parabola stuff. But for right now, hey, look, we just took, I'll scroll all the way up, we just took points in space. We said, I have a flat piece of space and I can lay down a point there. And that point can be represented by two numbers. I said, hey, you know what? We need to get used to this space. So all the things in the upper quadrant 1 are positive. All the things in quadrant 2 have a negative x and a positive y. All the things in quadrant 3 have a negative x and a negative y. And all the things in quadrant 4 have a positive x and a negative y. And so we know where we are relative to the origin if I see the pair of numbers. And then I said, hey, you know what? We had these expression things that we were using, and they had patterns to them. And we could sometimes see the patterns if we put them into a table. Well, if I let this expression thing equal my y value, that table becomes my points. And for the case of this expression here, we see it makes a line. I changed one thing on that expression and we got a different line. And we're really going to explore what it means to be a line in points in the next class. And to show you something different, I did something that wasn't a line. Yet you can still make a table and get an idea of what it was doing. It's coming down and then back up. Usually, the higher the power I see here, the more points I do to get an idea of what it's doing. Like I probably would have done a -3 and a +3 to get the one point up here and the other point back up here to get the idea of if it had an up and down. But that's something we'll learn as we play with these. But the idea is I can have any expression and I can visually see what it's doing. And I can start borrowing words that we have going up, coming down. And yes, we do tend to talk left to right, like we're reading. All right, so I'm going this way, so I'm coming up. I'm going this way, so this one's going down, and decreasing and increasing. And that's going to fall out to particular points of these expressions. It also falls out to particular things in word problems. And I really want to highlight that, as Teresa said, this thing that's called the slope is a rate of change. My answer comes out in y because rates are things we do a lot. I want to use that word also whenever we use slope. So you'll hear me say slope, rate of change, slope, rate of change, slope, rate of change, because that's going to give us something visual and a feel for some of the things we're doing. All right, that's the new material in the printed book. It is the printed book. Whoops, I flipped the page on the book and that gets hit. In the printed book, it is. Let me get my chapter number here. Chapter 10. Chapter 10, Section 1. And we're going to be jumping back and forth between 10 and 9, paralleling the things graphically and equation-wise. I wanted to get the graph drawn first so that we knew our places in the graph. And so this is Section 10.1. I will have the homework up for that for a week Sunday, right? Not this Sunday, but the following one. Focusing on graphing. As soon as you can start practicing it, please start practicing it. Get comfortable knowing where the points are on the graph, because I find it very, very useful when I look at mathematics to look at it, to look at things moving, instead of just playing with the equations. I do think we tend to think that everything you can do in mathematics you should be able to do with the equation, but some of the most useful stuff is actually coming from the graph and how the graph moves and interacts, and we can describe things. And so I'm trying to scroll up here. Type this in and I'll switch over to it. Okay, switchy. That's the wrong one. It's that one. There we go. And so, if you look up in the upper corner here, there is an expression, just like the expressions that we have had. It has a variable of x with large exponents. Now again, we will work on how to deal with exponents. We've already started, we'll continue that work. But if I'm able to graph it, I can see things it's doing. Like it turns back on itself and it has a high value here and a low value here if I'm in the middle. Otherwise it zooms off. And that's actually a load of information just from the visuals. And it means if I look at these numbers here, if I'm anywhere past 1, I don't have to worry about it turning. It's just shooting up. If I'm anywhere past -2, I don't have to worry about it turning. It's shooting down. These are things I'm seeing. And so if we can get this language to translate space into mathematical terms, we can let our data tell us what it's doing without having to play with the equations so much. And that is the true value of this. It's a pain to start with the mapping, and there's a lot of little things that will pop out of it that will build out. But if we can start with the basic idea that each point in space is 2 numbers, and then we're going to say, hey, each equation can be 2 numbers, a y value and that expression we were used to doing. All right, that's all I have for today. I'll get those homeworks and things up. If you have anything, please email me your questions. I'm trying to get to them. I have a question that Alec asked and Janine asked that I'm going to record 2 videos for and put up on the playlist. Actually, right when I'm done with this. So let me get this to switch back. Scroll down. There we go. Be safe, be well. Till again.